Let's get started here. So we're gonna have a panel here, a panel discussion with a number of our distinguished attendees here, and we will talk about processor trends and what that actually means for our software. So what I'm trying to coax out of them is a bit, like the idea of what's gonna come up and how will this impact us. We have on stage here Andy Warner. He's a distinguished technologist at HPE. He's also a board member, a governing board member of HPSF, and he's pushing us really hard to get this right, which I appreciate. He's been involved in lots of deployments of HPE, so he has a perspective on all the different processors, which is probably very valuable for this discussion. Then there is Michael James from Cerebras. He's a co-founder of Cerebras. Really exciting new architecture. I don't know if you've ever seen that thing, at supercomputing sometimes there's a chance. It's a ship like this big and you can actually, see it. It's not just this tiny little thing. It's really cool, but also has a lot of challenges for upcoming things. And never, it does, right? Would you agree?
We certainly have a different way of building the chip, and we think it should be exciting for this community.
I take that as a yes. We have another member here on the panel, also from a startup, NextSilicon. We are also doing interesting things in ways which are very different from how our chips, which we mostly use right now, look like. And I'm looking forward for his perspective. Then there's Kristi. Kristi's from Livermore. She's been working on Umpire, has been working with applications, has been trying to make these new architectures more usable, and will hopefully provide us with a perspective on how much these other people are talking stuff we can't really use, right? Because we don't know how. Okay, and then we have who else is on our list? Sorry. Barton Fiske. He's a senior alliance manager for the HPC developer toolchain, so he's from NVIDIA. So he's dealing, a lot, I guess, with users, and has a, represents here, one of the most established players in our field right now. And, people who want to sell us really, really expensive GPUs, and probably more of those in the future. And then we have Cornille from AMD, a member of technical staff there. He's working in data center GPU solutions, and they have sold us a lot of GPUs recently, and which we are trying to use. And so, to get this started, I came up with a bunch of questions, but you can add more questions there. What we're going to do throughout this panel is I will alternate between that and also asking in the audience, or if you just want to ask your questions in person, right, you can do that even if you entered that already there, so that we can have a bit of more of a discussion going. Okay, with that, let's get started. And my starter question for the panel was, what is the change in architecture coming up which will force us to do the most work in our applications and our algorithms, redesigning how we do things and impact, how we do things. Essentially, what's the bad thing coming at us we have to deal with in the next, 5 years or so? Andy, you want to start?
You're going to start this end? I would say two things in my mind. One thing HP does is we have visibility into lots of people's roadmaps, and I'm going to steer a million miles away from anyone else's roadmaps here. But two things that I think are already happening and we're not doing a good job of addressing. One is adequately using the new hardware that we're getting, and I'll return to that. But we're seeing a massive increase in operations we can get, but they're not floating point 64 or 32-bit floating points. We're doing a terrible job of adapting to that in the HPC community at the moment. And I think you heard me ask the question earlier about whether HPC Toolkit, whether there was anything about addressing dynamic range there. So the second is workflows to actually incorporate solutions like my next door neighbor here. I think we're doing a not great job of actually incorporating, creating software frameworks that allow us to seamlessly incorporate novel technologies along with mod sim that I will posit is not making the best use of the silicon that we can buy today, next year, the year after. So those are two huge challenges that are on deck today, and I don't think we're doing a good job of addressing.
Okay, thank you. Michael?
If I look at what's driving change in processors, is the end of Dennard scaling and artificial intelligence. And if I think back to when I was learning in the field, it was always, hey, Moore's law might one day come to an end, and that was scary. Like, what will anybody in computer science even do at that point? But the need for high performance is not going to go away. And artificial intelligence has provided a huge market driver. And so instead of being a field in stasis, what we've seen is quite the opposite. There's all of a sudden room for a lot of creativity. And it has hit the hardware space with the explosion of new processors, some of which I guess are causing a difficulty for this community in terms of how do you take those up and get their capabilities and the new things that they can offer. So I think we will see a ripple effect from the hardwares up into the software stack, because obviously you're not going to be inventing software methods before there are platforms so you can run them on. In terms of the future, I think that you're going to see even more continued innovation in hardware, that you will see devices embracing new ways of being built with photonics, with different memory technologies, with 3D stacking, with maybe analog or neuromorphic designs. And all of these things have some way to intersect with the type of physics simulations that this community runs.
Very good, thank you. Patrick?
Yeah, so one thing that we're really thinking about is the fact that, there's this problem of porting and all of this, and the idea that probably the software stack that we provide that needs to somehow better present an interface for the programmer. I think that a big place that this is going, and is sort of a continuation of what's already happened, is this move to more declarative type programming models. Right? I mean, a lot of the work for getting to GPUs was exposing the parallelism. It's really just Amdahl's law, right? And so I think that going to massively parallel systems, if you've rewritten your code or changed your algorithm in some way to sort of expose that to some framework like Cocos or something else, that really gives an opportunity for different vendors and different processor technologies to approach that differently. And I mean, one thing that we're really interested in is still floating point 64 performance. I mean, we're not giving up on that yet. So I don't think should be a foregone conclusion that somehow FP64 is dead.
Okay, very good. Kristi?
Yeah, so at Livermore, most of our focus has been on just preparing for LCAP and kind of dealing with this new single memory space situation. So I think, at least in my world, trying to make sure that our applications can handle the single memory space is right up there. But I mean, I completely agree with what's been said here previously. I think AI is definitely going to drive this rise of different processors. So, yeah, that is my 2 cents.
So, Barton.
Thanks for the opportunity to be here. Two things. One, the first thought that came to my mind for this question, which didn't come up in the notes that I was preparing, is quantum. And the amount of change that will ripple through the entire software ecosystem. As you know, NVIDIA has a quantum library, but we don't have a quantum computer. We're actually simulating quantum computers and getting iteratively better at it and faster at it. But when you look at the overall impact of how those algorithms are written and how the systems themselves are built, I think that has the biggest impact yet to be felt. The other area, I've heard the comments about photonics. I think that's an inevitability. You can only squeeze so many electrons through a wire, and we've really reached that point. So I think all vendors are going to have to face that. Most of my comments are as an industry person, not necessarily as an NVIDIAN. And energy efficiency, without a doubt, that is going to be what's driving all of us. All of our data centers are running out of power. We've conveniently thought that there was an infinite amount of power coming into these data centers. And the vanishing point being the power budget of the human brain, 12 to 15 watts. If we could get to that scale, that would be pretty impressive. So to me, energy efficiency and quantum are what I think are the two biggest shaping factors that vendors have to deal with and that the software will have to adapt to.
Okay. Brian, last one.
Yeah, I agree with most things that everyone said. To kind of distill down some of the points, you have to continue to make software sort of accelerator or coprocessor focused. So trying to remove more and more of the in-between work, and also making sure you're having enough work for your coprocessor or accelerator. And then lower precision data types. It's not just an AI thing. If you're using half or a quarter of the bits for any data, then that's double or quadruple the bandwidth. It's not just gem operations. There's fewer bits, fewer electricity, more energy efficient. So I think that's a big and upcoming way that that applications will squeeze more performance out of their limited resource budget.
Okay, thank you so much. So there's actually a couple topics which came up here, which already popped up on the question list, but also were in my list. And the first one, let's go back to that, and that's the question of FP64, right? So we've been relying on FP64 forever, right? And AI is obviously going in a very, very different direction, right? There are lots of chips now coming out, which don't have FP64 or have very little of it, right? And the question is, what I wrote down here is is this something we just have to get too used to? Is the cost of adding FP64 so high, that it's not worth it for chip makers? Is it something where, do we actually need that much FP64, right? A lot of our applications, also, for example, on AMD, right, are not actually FP64 limited in any shape or form, right? They are limited, as we may do way more memory ops, they do more integer ops than FP64, right? Mm-hmm. So how much of a problem is FP64, and is that something where we, how hard do we need to think of getting rid of that in our codes? Who wants to go first?
I can start since I brought it up. I think historically, FP64 has been semi-free, right? Once it was available in hardware, people just migrated towards it, and there hasn't been a lot of performance difference writing your app for targeting FP64 for a different data type. So you're like, well, I'm going to get my precision. With newer accelerators, and also as we're seeing the end of Moore's Law and need for higher efficiency, that calculus has to change. I think the HPC community needs to be more careful about their usage of higher precision. AMD doesn't see FP64 going away. There are applications that absolutely need it. You can't get around using it. I mean, if you have a system of equations that has a very high stiffness or certain properties, you need that precision. But there's a lot of work that hasn't been done in how much precision does my application actually need, and where is it needed? So more analysis will need to go into how can I get the quality of results that I need that represent my problem well, but use the fewest amount of precision resources.
So I'll return to my premise that in order to do that, we need software tools to track the dynamic range that we need at various points in algorithms, in libraries, or whatever. And there's nothing to actually say that, you know, BF16 is an optimal choice. There's nothing magical about them. That was just made up one day and is good enough. I want to steer away from the binary thing. Oh, FP64 is not going away, whatever. It's not being invested. People are, you know, the curve for performance from your guys' view for FP64 capabilities on chips is not doing this. You know, the fact that people may say, well, we'll keep FP64 around. It'll do something like this. The rest of the chip will be doing this. They're just not spending the gates and transistors doing FP64 anymore because we're not a big enough market. We have to write our software to use the silicon we're being given. I think Heidi said the same thing yesterday up on this stage. You know, we have to be thinking about what is the silicon we've got today and are going to have next year and for the next 5 years, and write software for that, not for some processor that was roaming the earth 15 years ago with more cores.
Yeah, the comment I wrote in my notes was the right tool for the right job. And the software world that we see today in no way resembles the world when FP64 was first imagined and brought into being. And so the marketplace is really demanding, you know, these variants. The amount of research that's going on, not just in HPC, but in AI, and the mix of precision and the mixed cases are forcing these design trade-offs of die space for registers and for floating point capability. So I think you'll see a broader mix of offerings. And I do agree, I think there is a need for FP64 in certain cases and in some workloads, and it shouldn't disappear from chips entirely. But I think you're just going to see all of the marketplace respond with a broader array of choices and capabilities.
Michael, Patrick, any comments from the startup scene?
I think if you look at the market drivers in AI, FP64 is basically irrelevant. There is a lot of pressure to go to smaller and smaller bit precision. And this, you know, it might be an oversight of, there's so much infatuation with these LLMs right now that maybe the AI community hasn't thought what would it take to bring AI and physics simulations together, and there could be a very rich AI space from that. I don't think that you have to worry about FP64 completely disappearing. I mean, the CPU guys can't even make the x86 instruction set disappear. It's just not going to be your highest performance route. That if you want all of the compute throughput, you should also think, how do you use the single precision, half precision, whatever names were given to 4 and 2-bit ops. But that also, there's, if I step beside this, there's sort of a cognitive bias that we all have. If you take something away from somebody, that's hugely upsetting. But there's another thing that the scientific computing community needs, and that's bandwidth. And we've been without bandwidth in our applications for a long time because the memory is on separate chips. You go through some tiny conduit. And so we've been living in this world where compute is basically free and communication is so expensive that you go to an SPMV and you get less than 1%. And these AI platforms, a lot of them can actually deliver the memory bandwidth. They use fundamentally different ways of integrating the bandwidth. And so I don't think that it has to be the glass is all draining out. That there will still be new and creative uses for scientific computing, even with the AI chips.
Yeah, so one thing I'm sort of thinking about, especially this discussion about bandwidth, which I just find is an interesting question, is whether, so at some level, if you need two single precision numbers to get the same physics as a single double precision, if you're bandwidth limited, are you actually getting ahead? That kind of question. But yeah, I think the thing is that in this world where we're bandwidth limited, if you're in an architecture where, yeah, you have to go back to HBM even, every time you do some operation, you're very register limited. I think that bandwidth issue really is part of what drives the move to lower precision. I would expect that, so we have a very different architecture. It's a sort of flow-based architecture, and we think that we can do better in terms of how the floating point performance goes because of where and how we move the data.
Do you think, that was a question from the audience, do you think that emulation is a way for FP64? As that you emulate it on the chip, through, I don't know, just using large integers or whatever, right?
I mean, in some sense, then that's just that it's FP64. This would be, I think, our take is, that the software stack should be smart enough to use the hardware resources relatively efficiently. And so if it's efficient to emulate FP64, then that should be something that either the runtime or the hardware itself is doing and deciding. In that case, okay, it looks like it has good FP64 performance as far as the programmer is concerned.
Kristi, what do you think your application people say to all of this?
Yeah, just in terms of some of the applications at the lab, really the precision is non-negotiable for certain applications. And so from that point of view, I'd have to agree with Brian that FP64 isn't going anywhere. Though, we can kind of meet in the middle and, use something else for the non-critical calculations that people have. So even at the lab, there are plenty of areas where you don't need full FP64 all the time, but in certain applications you do. And I mean, as an application developer, you just know you need to get a certain amount of precision, and whatever chip is going to get you that's what you want. And you don't really care too much about some of these other great and wonderful things that you could take advantage of. You just know, this is what my application needs to do. This chip is going to get me there, and so that's the one I'm going to use. But I definitely don't see it going anywhere anytime soon. Though then again, we are using AMD for LCAP.
And to follow up on what Kristi is saying, you should always do what's right for your numerical application. If the fundamental science, because the fineness of your quantization requires FP64, you should design there first, and then think, how do I get the highest performance? And if there's a mixed precision way to optimize that, or if you can emulate the FP64, those can be acceptable techniques. But you don't want to start with something that is super high performance, but doesn't converge or get you the results you want. So you're not just going for what is the frequency of the processor, but what is the best time to solution. And you're probably using FP64 a lot because it is an easy fallback solution that lets you write your first code and not worry about all these convergence issues. you still want to do that first, but then you also want to see, oh, here's this big engine. How do I make the most of it? And so after things are working, start migrating onto the highest performance data paths that you have, and get some performance telemetry in there. See if you're using all that dynamic range, or there are other ways that you can tune your algorithms.
Okay, before I dive deeper into the audience question, I want to bring a follow-up on one topic here. You know, a lot of people brought up memory bandwidth. You know, memory. Brought up like Ovid and Cerebras. Now we have this kind of more distributed memory system, right? When we think back a few years, right, or maybe for some people it's more than a few years. Like, you know, go back to before Sierra and Summit, right? There was a big promise coming from NVIDIA and saying like, oh, we're going to do unified memory, right? It's all going to be kind of like coherent. And, you know, we got a huge jump in Sierra and Summit in terms of connectivity, right, with NVLink. And that was great, right? But the unified memory promise, I think, didn't pan out as we hoped, right? I'm going to ask Kristi about what her thoughts on that are in a minute. Now we got El Capitan, right, which actually has true unified memory. It's physically the same memory, right? But we also don't have any kind of like roadmap which says, oh, there's more of these APUs coming, right? Because the AI market is not using it, right? They use the discrete GPUs where you don't have this unified memory, right? And then there's the issue of the question, oh, do we need this kind of extreme NUMA stuff, right, to get actual performance, right? And these two paths, in my mind, clash a bit, right? So where are we with that, right? Is unified memory real, right? When is it real? Or do we need to completely give up and prepare for in 10 years, the only thing we get is, you know, megabyte size slices of memory for each of our cores, and they need to talk with message passing to each other. What is the challenges there, right? What do you think physics is going to drive us to? But before that, let's start with Kristi. What's your take on unified memory?
I'd have to agree that it didn't really pan out the way it was promised. And I mean, I don't think a lot of people at the lab actually use unified memory, even on, you know, Sierra, because there's too much of a performance trade-off. So we find other ways to get that performance using Umpire. And then when we went to El Capitan and we had the single memory space, that was something that we had to account for in the tools like Raja and Umpire. We had to actually program for that and work around it and try to make it performant for what we were doing. So we made things resource aware to try and make sure that the host and device aren't stepping over each other in this single memory space world. But then again, yeah, there is no successor to that we know of. I mean, we're all focused on LCAP, you know, that is taking up most of our minds. So we're not even there yet. But it will be interesting to see if everything that we've done to accommodate for the single memory space environment will change later, and then maybe some of that won't really be necessary anymore. But I think what's really important is the partnerships with the vendors. So what we've done with El Capitan and trying to prepare for that has been a lot of back and forth with the vendors where they say, oh, this will be great and awesome. And then we go and we start looking at it and we're like, it's not great nor awesome, but you know, let's try. And then, so it's a lot of back and forth, but it's that partnership that's really important so that the applications can actually see the benefits that are promised. So, yeah.
I would say the devil's in the details with sort of a unified memory architecture. Even if you've got a system which, you know, perhaps has, you know, HBM right next to GPUs and has some other memory, but it all appears in some kind of common space. If it's not well implemented, you wake up one day and find out you've got your Linux disk block cache living in your GPU's HBM, and that's a really bad day. And you find you can't evict it. That sucks, and that's a real-world example. When you wake up and figure that, suddenly the unified memory doesn't seem like such a great idea. You paid a lot for that memory, you want your algorithms to use it, and it's busy, keeping inodes.
Yeah. I mean, on LCAP, we do that, right? Because that's the only memory.
Yeah.
But that's the memory you've got, that's fine. I'm not talking about LCAP.
Yeah, no, I know. Anyone else?
This concept of unified memory is sort of the old guard. The way we used to do things is try to make life very easy for the programmer, and that is what a CPU is. There's a huge amount of circuits to emulate the execution environment, to hide the fact that there's a memory hierarchy, but what your application does is it occasionally suffers a cache miss, and it looks like a non-determinism in the performance of what you're running. And there's a role for that. If you want easy application development, then fine. Go write a little bit of pseudocode. I run it on the CPU. That will probably always be everybody's first choice when they're just tinkering at a small scale. When we care about performance, and especially some of these new processors, we're in the business of constructing machines that use the laws of physics to get you the absolute most you can. And there's a fundamental limiter. Most of us know about the speed of light, and is actually fairly slow on the time scales and frequencies that we deal with. And if you want to put a big unified memory there, you will have to pay performance for that. Now, when I think of what are these machines trying to do from a HPC perspective, there are common attributes that hit all of them. Essentially, we have linear accelerators. That's an FMEC. So at the heart of all of these algorithms are linear methods. And then there's some matrix structure, and we have to realize the interaction matrix over whatever interconnection topology we have. And that's going to call in a whole bunch of data movement. And then we still need our algorithms to be extensible, and so all of the machines are programmable. And I don't think that anybody is going to ever sell, here's a one-purpose, fixed-only function device, especially into the HPC space. They all need some way to reconfigure their matrix and have algorithmic expressibility over the FMEX.
Not going to do ASICs. Right. HPC is never going to do ASICs.
Yes. They will be programmable processors. So, what's driving at least our designs towards a very localized memory is all of this. You get huge bandwidth by the locality. The latency is low. You're paying less energy to move the bits from where they're stored into the execution complex. And we have removed the memory controller from being the hub that interconnects all of the devices. So if you look at the exascale machines, you have these little islands of compute. They're fast clocked processors. They go through some huge bottleneck, but they hit the memory controller to talk to the peripherals, to talk to everything else, and that pushes you into these really bulk access patterns. You need to load a contiguous block of data. You need to operate on that for a period of time, and it's sort of this slow postal system amongst stranded processors. And when you instead look how you can manufacture, if you interleave everything, you can get much finer grain activity on the chip. And what that ultimately gives you is the ability also to have strong scaling in the application. So you can do things that are fine grain and get better time scale out of the solutions instead of just hundreds of iterations per second. Maybe you can see millions of iterations per second from your simulation. But there's a cost to that and how you organize all of the software. And as you strong scale a lot of the programmable elements, they can pop out. So just even a loop induction variable might become performance critical if you don't have a lot of work to amortize over the individual cores.
Yeah, and when we talk about unified memory, it also depends what kind of properties you're interested in. So the MI300A and LCAP has certain properties by being physically unified memory. There's still under the hood, there's like separate page tables for the CPU and the GPU. So nothing is ever free, right? And so if your view from an application is, I don't want to be careful, and I want everything, I don't want to be careful about where I put my memory or where it's used, you're going to pay a performance penalty for that. But on the other hand, if you're careful about where you're using your memory, even unified memory on like Sierra, where the pages are managed, as long as you're careful about it and cost can be amortized, that works fine. So it's really that balance of what amount of effort do I need to put in my application to use the hardware versus how much of the hardware performance do I really need for my application.
Yeah, I would say that the sweet spot is probably something where it'll run with unified memory and the performance may not be optimal. And most of your code, you can let the unified memory do its thing, and instead, just if you have some critical region where you say, oh, the unified memory manager is not really doing a very good job. Let me tell it more, either tell it more or manually manage it in some way. I think that's one thing with unified memory is it's often a binary choice of either I run in UVM mode or I don't. And so I think that trying to get the benefits of both with the software stack is also a direction.
And I think this is where things like Umpire can come in. Your compiler or Linux provided allocator is probably not going to do the right thing for when you're working with an accelerator.
Does AI actually use unified memory? Does anybody know? My question was, does AI actually use unified memory?
I don't
AI
think
algorithms?
so.
TensorFlow, any of that?
They usually have to manually stage data to the CPU and then the GPU and carefully do that. And then asynchronously.
It's down to the programmer's choice. And I'm going to go a little meta here, and I do want to say I'm speaking as an industry practitioner, not an NVIDIA employee, so I'm not saying what NVIDIA's position here is. But memory is a software problem, frankly, meaning that I think one of the biggest mistakes that was ever made in computer design was allowing humans to allocate memory. It is a solvable problem that is a characteristic of the machine that's running. And compilers and drivers and software should be capable of monitoring the workload, being informed about what kind of workload is being put together, and then allocate the memory as needed dynamically and adapt to the workload. Having humans allocate memory is just, it's a legacy, without being too pointed on the point. And so I think AI and informed systems have a lot to offer there. I think there is progress that should be possible, and that there should be some standardization around it in the industry. There should be ways of taking memory allocation out of humans' hands and giving it to the compiler. I'm the one that asked the Rust question yesterday. So I found that particularly intriguing as I learned more about Rust, and that memory is something that actually could be taken away from the programmer. And I'll end this comment with, we are on the dawn of a confidential computing era, or whatever you want to call it. But there are very few facilities in this room that are going to accept a system that is not end-to-end encrypted. And memory management and memory mangling needs to be much harder than it is today in order to deliver that guarantee of an encrypted end-to-end solution. So I think it's an inevitability, but I don't think the vendors or the industry in general are ready for it. And I know as programmers or as developers, we probably don't love that idea.
Okay, I'm going to go in a few audience questions now. And if this is your question and you want to kind of follow up on the question a bit more details, raise your hand, please. So here was a question for researchers writing simulation codes, right? How do we keep up with the rapid hardware, software changes, right? And if I'm allowed to interpret that a bit, what can I do today, right, to prepare myself to be a bit more agile, for the upcoming changes and, the evolution of hardware?
So I would say the most important thing is probably to think more declarative than imperative. That is, instead of writing your code in such a way that you are saying, do this, and then this, and then this, here's all the detailed structure of how I want this to be executed. Phrasing it in terms of, algorithms like, sort of map, reduce type phrasing or a way of thinking about it, really then gives you the most flexibility. You've expressed, okay, this stuff is in parallel, there are no data dependencies between it, and this stuff has to be done this is in larger chunks where the data dependencies are, where the independence is. And if you use something, I'll point out Cocos, for example, but there are many of these that where you're sort of declaring more what you want done rather than how or where. That gives you the most flexibility in terms of some new architecture comes out and, my algorithm is already parallel and I've already expressed that, and now the library or the runtime can exploit that.
Any other thoughts? Or is it just a too hard question?
I think there is a lot on the vendors who are providing these new architecture types. It's really kind of on them to give us some good documentation on how this stuff works. The talk this morning where John was listing out all of these questions about your communication patterns and where are these certain things living that you might want to optimize. All of that stuff is a lot harder to find than I think it should be. And there are reasons for that, but all of that makes it hard for developers to even put themselves in a position to be able to handle all of this new hardware that's being thrown at us. And then there's just inevitably going to be a lag period where it's a great and wonderful new hardware that's come out, but we're not going to adopt it anytime soon because we haven't caught up yet. Well, at least for the lab, I think that's also purposeful because we want to make sure that it's going to be a worthwhile investment if we decide to go down that path and try to adopt some of these new hardware. So I think, there's something to be done for the developers who are actually trying to develop these applications. But there is definitely a lot on the vendor side to help out with preparing for these new architectures.
Yeah, I think the important part of that is, to be a successful programmer, you have to have some kind of mental model of what's going on underneath. And especially if you have a very different architecture, people's mental models are probably wrong that they immediately construct. And so you need to have good tools and good documentation to make sure that people are thinking about it close to reality.
We've seen a lot of success with a co-design approach, and so at Cerebras, when we get a new application, we like to talk with the people who are actually doing the numeric algorithms. Ask what are the fundamental drivers? What is the you've given a 10-dimensional problem, but which ones of these actually matter? If I could stretch something by an order of magnitude, what would you choose first? And then there's sort of a geometric embedding process where you take the algorithm, which has a bunch of math, some of it dependent on others, and try to actually map that onto a complex of chips. In our case, different parts of this dinner plate sized chip, or even a facility full of them. And in that process, there's opportunity for the hardware group to learn about the applications, as well as for the application group to understand what is the equipment that you're working on. And I think we've even learned from seeing some of the more complex ways that HPC algorithms run, things that were very relevant in the AI space. And so we have a better AI product for having gone through the co-design exercise. And at the same time, we've seen, at least for the slices we've looked at, a very huge performance differential based on understanding what is the topology of the system and how does the algorithm sort of naturally fit versus just taking a pre-existing code, trying to hit compile and saying, well, you got whatever the compiler knew, because the compiler probably didn't have innate knowledge of the new architecture, specialist knowledge of the algorithm. It's just doing the imperative thing. And so I think in the teams of the future, I try to find those people who beyond software also know and are comfortable kind of brainstorming what are the possibilities in the hardware space, and there's a lot of performance potential there.
Yeah, I want to reiterate that. I mean, I've been lucky enough to see firsthand multiple examples. So if you're tasked with writing a library or an application, I encourage you to actually reach out to the vendors and talk about your problem, not about where you are kind of as you've thought about it with the silicon you've got today and the tools you've got today. Talk about your high-level problem. Back up a couple of notches instead of saying, well, I'm doing this and I've hit this boundary, and from what I know of your next chip, it's going to behave this way. Talk about the actual problem you're trying to solve, and work with the vendors so that they can come back and say, actually, you're going about this the wrong way. There's a better way to do this. And we're thinking of this functional unit. Would that be useful? So I just encourage you to have those. Try and find the space and get the sponsors to have those conversations.
I heard here two things, right? And in some ways they're a little bit contradictory, and it comes actually back to the most upvoted question right now, right? On one hand, I heard, just use this kind of general, reduce
Yep.
map algorithms, express all your parallelism, right? And then, somebody can figure out how to do this underneath, right? But on the other hand, I hear talk to every vendor, right? Like talk to every one of these things, understand every one of these architectures, and then figure out what the best way to go is, right?
I don't think they have to be mutually exclusive. You can talk to them, but don't expect them to build a chip just for you.
No, I get that, right? But the thing is, in some ways, that's a question between, how much generality can there be, and how much do I need to specialize in order to actually get performance out of chips, right? And there's a tension there, right? How do we deal with that, right? Do we have enough bandwidth to even do that, right? If if our co-design team from DOE goes to a vendor, right? Yes, we have the bandwidth to do that, right? But do we have that for every app? Do we have that for people outside of DOE, right? Do we have enough people who can learn all of this? So how do we deal with that tension between generality and the need to specialize in order to get really performance?
So an interesting thought I have is we do have these performance portal frameworks like Cocos. For applications, those can be kind of a big undertaking to bring them into their applications. Something more lightweight is like OpenMP or OpenACC. But those do have some challenges taking... those have challenges taking advantage of up-and-coming hardware and aren't always supported by the vendors. And when you want to get the most out of hardware, you usually end up resorting to some sort of kernel language or grid language like CUDA or HIP or SYCL. And one thing that's missing is some shared language, kernel language between hardware vendors. And it's maybe challenging to think about how one might design a kernel language that is extensible to various different architectures, but the concept of this is my single unit of work, and then I have some invocation that tells you how to map it to the hardware is the more kind of performant way to program for hardware, specific hardware, than kind of the here's my big loop, make it go.
Well, I'll challenge you. I mean, don't take this the wrong way, but wasn't that a plea for a miracle happens here, somewhere in that? I mean, I'm just, we've been doing software development for 50, 60, 70 years, 80 years maybe, and, I'm not sure we're there yet for performance stuff. You could ask that question if you didn't care about performance, probably. It's the state of the art now that you can ask that question and get something that performs well. I don't know.
So I'll take a more sociological crack at this question, and for the person or the people that are asking this question, I feel your pain, very much so. And I guess the way I'd look at it is for stuff that's in production, stick with what works. You've got to get to science, you've got to produce results, you've got to get an answer. So don't stray too far from the things that you already know, that you put into practice, that you understand well. And very few of you are in isolation here. Most of you work on teams or work in teams. So then the next part of the answer, the response is invest in the next generation. They don't know what they don't know. They don't realize that this is new stuff, and they live to take on new interfaces, new APIs, new technologies. Put them in a sandbox and take small, well-defined problems that resemble the workloads that you have and let them have a crack at solving those problems with these new technologies and see if that's adoptable at a wider scale. But at the rate that I see innovation happening, it's exploding in our industry. There's absolutely no way any single one of us could stay on top of every technical innovation and then map that to the job that they're trying to do today. So I'm a very strong believer. When I joined NVIDIA, I was assigned to work in the higher education world. I had every university east of Mississippi and all of Canada as my schools. And what I realized was the rate of change is just absolutely exploding. And we can't stay on top of it. So invest in the next generation, give them jobs, give them things to do, and help them solve your problems.
Kristi came armed with these BS tags, so I'll try to refrain from making a generic claim here. But I can illustrate an example of the type of things we learned by looking at specific applications. And so we saw a plot of Quicksilver performance earlier in one of the talks, and it was predominantly idle. And so we've looked at this as a Monte Carlo particle transport application. And something that wasn't obvious from the application side at first is that this is actually a problem in bisection bandwidth. And it's not clear. So you have a bunch of particles that are moving throughout a mesh. And fine, you want to let them stochastically act according to some laws of physics. Why should this be bisection bandwidth? Well, it's because there's a big several gigabyte state table about what that physics is. And you also have a big mesh because you want your high resolution and accurate answer. And so if you actually look at the interconnection graph, how memory connects to the processors, you constantly have to be moving the particles through this mesh, and then you just say, well, based on my energy, what is this? And so this is an any-to-any communication pattern, and if you see the fundamentals going through the mapping exercise there, you can ask, how do I design the whole thing so that I'm not just doing A of I, access the ith entry of this array, but build this as something that the whole infrastructure can see as a distributed communication problem. And I don't think you can just map reduce it. You might want to say, here's the map reduced version of the algorithm, but if you want the most that your vendor can give you in performance, it helps to pull out the fundamentals of what that problem was, and that's the type of insight that we get by having co-design between the physicists and the hardware vendors.
But
and because it was a fact-based story, I'm immune to the BS.
The BS call was for like, I think our 7 years of trying an ECP to get OpenMP to work, showed us that it's not just a simple sprinkle it somewhere thing.
I was saying exactly that, I hope. Maybe that wasn't clear.
Yeah. Okay. There is actually a question which follows up on what you said. So you said in Quicksilver, right? It's really hard to understand, or it's not obvious that what is happening is this bisection bandwidth problem, right? What information from developers and users, right, would actually be helpful, to better understand what's going on and what the needs are of applications, right? What kind of things could we get from how could we extract information or curate information on these apps, that we can get the information we need to inform this co-design and inform, like how we get better performance out of this.
Do you really want that, or do you just want better telemetry from the silicon? Because when it's actually mapping it onto something. And I think we heard the plea earlier to say we're falling short in that area because we're pursuing other avenues right now and not really prizing observability. That was one of my takeaways.
Yeah, I think in the whole telemetry thing, so I go back to the lab again. We don't always have the luxury of turning that kind of stuff on, or so it really kind of goes back to partnerships with the vendors and having them understand that we really need really good debug information. And then I'll go back to single memory space because now it opens up a whole new world of problems, and you get these errors, fatal error, doom, and it's like, okay, thanks. But to have good debug information is extremely important. But I think for us, the labs, where not everything is open source, I think just having the partnerships with the vendors that you're working with and just collaborating on certain things that you need, that really good debug information so that you can figure out what's going on under the hood, because it's all very complex. And like Barton was saying, we just can't keep up with everything, with the rate of change. But I think that's at least one thing that we can do is the partnerships.
Speaking as a vendor, I know I'm asking for something that's not actually probably practical, but more transparency into the workloads and into the codes. A lot of our systems end up behind air-gapped walls, and we never actually get to see inside them. And when asked for that, it's like, oh no, can't give you that. And so there is some tension there, and I don't know where the middle ground is. But if we were to just turn on full-on tracing and ask you to send that stuff to us, maybe we could make some progress. But it is a bit of a challenge. There's a certain amount of distance that's there by design, and very much a human regulatory problem, understood, but it is part of why these things exist. And I completely agree, better debug is on every vendor to do a better job there. We've just sort of forgotten about the need for that and just assume that the system will take care of itself.
No, you didn't forget. We got printf even in CUDA like 1, right?
So printf is your friend, absolutely.
Performance telemetry is really important. That lets you see what's happening. And the other side of that is having a simple hardware architecture. The more levels of hierarchy you have, and the more ad hoc mechanisms are built into the chip, the more difficult it is to interpret and to understand what the fundamental performance driver is. And so, if you as you build things closer, and if there's a way to go to a homogeneous structure, then actually some of the higher level questions we have get simpler to answer. And so you should be asking when you go through a performance telemetry exercise, even supposing that you did get all the visibility you want, were the data interpretable in a way that you can understand how it links to the fundamentals of your application. I think that's the standard we should hold our hardware architectures to, as well as just this broader performance debugging landscape.
What there's an onus on the software libraries to help with that mapping, right?
Absolutely. I think the presentation we had saying that here's statistical sampling, and we're going to use this without changing the code to get a picture of the entire runtime is terrific, and that presumably doesn't require you to go put in hooks everywhere. And I think that we should even see floating point range. If the mapping from the conceptual algorithm to how it's instantiated on hardware is done in a theoretically straightforward enough way, I can say, oh, when I peaked this value in memory, that was that variable. I can then statistically sample a dynamic range too. And it's hard if what I sampled was something that maybe or maybe not was evicted from a cache and so forth. So sometimes as we build, we don't want to just add on gizmos and complexity. We want to think, how can we make a consistent space for the algorithm to run throughout the large hardware complex?
So I want to add two things. One is short response, which is there's a really nice article from a few years ago called "C is not a low-level language. Your computer is not a fast PDP-11," which is a really nice discussion about, especially with CPU design, how we got in this situation of basically trying to emulate a PDP-11 that's going really fast and hiding all of the complexity of how the processor actually works. And it was actually in the context of Meltdown Inspector, right? That this is side effects of trying to pretend that there's a flat address space, for instance. But then the other thing I want to point out for us is that we have a big push and a big emphasis on adaptive optimization, sort of profile-guided optimization type thing. So like the hardware is very much designed with telemetry and all of this in as a basic part of what it's doing, which means that we do have a lot of very detailed information about what's going on in the hardware, and that can be exposed. And so, if you have hardware where profiling and telemetry is a sort of first-class design feature that can make a big difference when you try to understand what's going well and what's going poorly.
So one word which hasn't come up yet is risk, or better RISC-V, right? Is that something, is that a thing, right? Is that something we expect, to show up on our doorsteps? If it does so, does it change how we play the game, how we write our software, what we need to think about? Or is it just, a different CPU architecture and, the compiler takes care of everything?
So I think I'm allowed to say that we are using RISC cores as part of our hardware design. So it is a real thing. We're not using them for everything, but from what I can tell, it's a real thing. It's coming. It's not clear to me that it's really that much different from sort of the transition to ARM, in the sense that, yeah, it's a RISC machine, but not RISC-V, RISC in the generic sense. But I'm not convinced that it's going to have a huge impact in terms of at least applications.
I don't think we're ready for it, to be honest. And I actually double-checked my stats for this before this. So, there's supposedly a RISC-V internal architecture update every 12 months, but for the last N years, there's been one extension per month, basically, has been proposed and implemented. And right now it takes 2 to 3 quarters to push something into the Linux kernel. And so the cadence of the RISC-V ecosystem simply does not match even the Linux substrate that we want to run on, let alone the libraries, let alone all of the stuff we layer on top of it. There is such an impedance mismatch between these two ecosystems. We buy machines that need to run for 5 years, right, as a rule, just because of the investment in them. So it's a very strange space. You've got to be incredibly careful because it is something of the Wild West. I think it is subtly different from ARM because ARM's a very thoughtful, controlled, deliberative ecosystem. Whereas you can get a RISC chip that it'll support, out of order access, and then you'll get another one that doesn't. And, you can get completely different results from these two different chips, simply because they've chosen to implement different things. And the cadence that market operates at is just inconceivable for our market. So, I don't think we're ready for it, frankly.
As long as you give us lots of good debug information and things are really well documented so that we can use AI tools to figure out what's going wrong, and help us, then sure.
Yeah, I'm not sure most people realize NVIDIA shipped over 1 billion RISC cores in 2024.
Yes, we don't.
Since the Turing generation, there's been a RISC processor on all of the data center GPUs. It's essentially our out-of-band management. It's how you communicate with the GPU outside of it. So again, I'll go back to the right tool for the right job. It fits a need, it solves a problem, and it's easily implemented. Obviously, I can't speak to features at the data center scale, but I will also say that if you're thinking globally, there's a compute problem globally, and if the rest of the planet doesn't like the architectures that are out there, they're going to invest and build their own. And RISC-V is an architecture that you can do that with. The problem is you bifurcated the entire space. There's no central one entity controlling its design and its implementation. And so, the gods help the programmers out there that have to program those architectures when they become available. It is an alternative. It is an alternative. I don't know that it's viable at a data center scale where you would build an entire data center built out of RISC-V computers.
Right. I think there's a big difference between is RISC-V part of something else, or are you talking about a RISC-V CPU and you're just running Linux directly on it? I think there are lots of different ways that RISC is being used. And
well, I for one would be really happy to see 8051s banished off the face of the earth and replaced by RISC-V cores, personally. So the other thing is they're eliminating the core tax. I mean, there's silicon roaming this earth in various forms with thousands of cores, thousands of RISC-V cores, and they've eliminated the core tax completely. Now, is that applicable to us for HPC? Clearly you're not going to get your memory bandwidth for 2,000 cores going in and out of the chip, but is it still useful memory bandwidth for 200 cores, and the other 1,800 cores can be doing something else? I don't know, but it's a different way of thinking about the problem space. Very different.
So here's a very forward-looking question. Today's HPC hardware is essentially coming from AI, right, or subsidized by AI. Yesterday it was from gaming. I mean, at least for the ones of us who were brave enough to deal with GPUs, like 5 years ago or 10 years ago. And the day before from like personal computing, right, or servers, right? Where will next generation's HPC come from?
If I knew the answer to that, I'd be sitting on a beach in the Bahamas somewhere.
That's what I thought.
I think we still have several more iterations of AI processors, and I can just say, without disclosing everything, that if I look at some of the chips we're using today are going to seem quaint by tomorrow's standards, and that's because the reach of AI, even with everything happening at its space, is still at its beginning. These LLMs are kind of like the existence proof that AI methods are interesting, and as we bring them onto problems that have greater dimensionality, like 3D simulations and other things where you need agents that aren't just text or high latency, still image-based systems, we're going to see even much more information processing. So I think also tomorrow's systems, I would double down on the AI answer.
I actually had a question, which goes in that direction as well, right? For a long time, we used effectively the same chips as, almost all the data centers were running, right? Like everybody was running, some Xeons or Epics or whatnot, right? And for the most part, other than the, few GPU machines we had like 8 years ago already, right? We were using basically the same chips, right? Now, it's starting to change, right? But that workload space still exists, right? Is that kind of bifurcation that we're not just using what everybody uses to run their web servers a problem for us? Or is our alignment with AI good enough that, we can get away with that?
Well, certainly in the time of the data centers, the conventional wisdom was HPC was like Formula One, right? It was like, okay, we were using x86, and it was like the stuff we were doing in HPC would trickle down to the data center. We weren't and then suddenly, trickle down to servers. Then suddenly data centers became, the hyperscalers became the financial engine that drove the silicon industry, and now AI's the financial engine that's driving the silicon industry, right? We're no longer, there's 2 generations where we haven't been the Formula One. Now, it's interesting for me to see at the system level a lot of AI things coming along saying, we're hitting the same problems HPC's been hitting. Script, because the laws of physics. AI doesn't get to invent their own laws of physics, right? So,
I thought some LLMs do.
Well, yeah, that's because they hallucinate, right? Yeah, but anyway, I digress.
Okay. Wait, which question? The question I wanted to ask. Everything changes here because people are upvoting things. And when I can't find the question I was just looking for.
Have you got sympathy for Todd now? Because this is role reversal. You were sitting there yesterday.
I don't know.
I'll address that last question while you're looking, which is just sitting here pondering, if you added up the compute capability of every mobile phone in this room, you would have a supercomputer. I have a colleague from my days at Sun, Adrian Cocroft, who worked on a paper and started that notion, and there's lots of other people doing that. So I would say, with the explosion of AI, what will be driving the HPC systems in the future are going to come very much from the edge and come from technologies that deal with data movement and data facilitation. There's just so much data out there, and that's why we have AI. If we didn't have labeled data, we wouldn't know what a cat looked like on the internet, or how to find one if we wanted to find one. And so with this explosion of data and with the need to find the needles in the haystack, data movement, data management, and being able to aggregate large numbers of capable devices. Would you be willing to give up your mobile to cure cancer? I might give up a couple of slices of capability on my phone if I knew I wasn't going to be invaded. But there's a lot of compute capability out there, more than the power that goes into our data centers can solve. So I think that is partly where architectures of the future and software of the future needs to address.
Okay, I found the question I want to ask. So there was a question today: the software is critical for successful systems, right? The system, software, the tool chains, etc.
Sorry, did you say pretty good?
No, but I said we are critical for.
Oh, critical. I thought you said pretty good.
Success. Yeah.
So critical.
We are not. We may be pretty good in US speak, but not in German speak. But one question is, right? How can all these different software vendors or hardware vendors survive, right? If all their programming systems are different, right? Is there enough critical mass behind that? Does it just not matter because you only need the 5 people who implement TensorFlow, and the rest of us, can figure it out, right? How does that work, right? If everybody does their own kind of way of doing things.
I mean, I would say that, and I'm going to try not to get a red card, but I think that an important place here is open standards. I think the goal of OpenMP was that you have some standardized set of tools.
I like how careful you're phrasing this.
And of course that was also the goal of OpenACC and and OpenCL and all of these. I think that effort, I would like to see more convergence on sort of these open standards. I was actually the one who asked the question yesterday about what role do language standards committees play, because in some sense that's a big stamp on sort of a particular, let's converge on at least some syntax or some set of algorithms. I think that there's a role to play there as well. I don't know if language committees are the right venue for the reasons discussed yesterday, right?
Since you asked the question yesterday, what do you feel about the answer today? The 2 highest velocity environments today, Python and Nickel, neither of which are within a country mile of a standards body.
So I know that at this point Python is consensus-based, right? They have a governing board that decides on PEP, on proposals. But I think a lot of that was that Python, for instance, had a benevolent dictator for life. So I'm not sure, I think is the answer, because Python has been very successful. It's not clear to me that that's because of the way it's standardized or not, right? It is, and part of that I think is that Python has a single implementation functionally, right?
Maybe the question wasn't so much about Python itself as a syntax, but about Python as an ecosystem.
Right, well that's what I mean, is that I wonder how much of the fact that CPython is so dominant in terms of there's basically one vendor, one project that everyone has settled on. So there's the question of, well, if you had to have different vendors all implementing their own Python for different hardware, would the same thing have happened?
Michael, I know you have thoughts on this.
If you look at how the community got here, we've been going through decades of Moore's law scaling, and forever you could just wait, the processor gets faster, and in the meantime we're going to grow complexity in the software stack, and they do more and more cool things, but a huge tree has taken root, and is probably not a tenable world that you take every application and rewrite it for every next hardware. It's clear that's a lot of what this community and the work projects we've been looking at are dealing with these problems. But at the same time, languages aren't fixed, and I think most of us can remember a time before Python existed. And what causes new tools and techniques to come into existence is you're going to have a driving performance need, and there has to be an easy enough ecosystem to say, I had a way of expressing this numerical algorithm, and wow, I got really amazing performance out of it. And if you have that, and you allow the same creativity that we've been using for a long time to ask, what other algorithms in compiler or just understanding the whole system flow and mapping to the resources we have can now automate these very high performance exemplars to become things that are new cross paradigm available. I think that a future is possible there too. And we don't have to imagine that the exact thing we have today is fixed for all time. So just as the processes are innovating, there's a lot of innovators sitting in this room, and I would say use the new architectures that are there to explore maybe not to your most complex versions of the problems at first, but interesting ones, and ask if you got a performance lever that actually moves the state of your field enough to bring some new tool into existence.
Any thoughts from you, Barton? Considering that, CUDA is probably one of the best examples of something where was a new tool, right? Which gave you real great a jump in performance, right, and had enough incentive to be adopted and got adopted, right?
Yeah, I'll borrow from an old saying from Sun, which is agree on standards and compete on the implementation. Meaning that, when I was selling workstations for Sun and I had to benchmark Pro Engineer for Kodak, there were 6 workstations. There was SGI, there was Sun, there was IBM, there was HP, there was a Windows workstation hoping to win, and an Apple somewhere in the corner. And it was literally choking the ISV ecosystem because they all had to write the same code base, but they had to compile for test and bug fix on 6 different platforms. That's collapsed now down to basically 2 operating systems, and those vendors can take those resources, that time, and that money and innovate in new features that are common. At the same time, there's this whole array of hardware architectures out there that will run under those operating systems and deliver, hopefully, reliable price performance depending on where you're aiming. So NVIDIA has always been in support of, well, not always, I will say is in support of open standards and looks to participate in looks at it from a platform-wide level. So,
So it'll be open standards like CUDA and Nickel?
Open source software to the degree that it benefits the community overall.
Where was the red flag?
That's a question beyond my pay grade.
That's the universe that this room exists in, right?
I understand.
I participate in both the Fortran and OpenMP standards committees. Being part of a standardization process, it doesn't feel like they're going to lead the solutions before they're developed. They may adopt commonly used patterns of solutions, and this is the same how Cocos solutions will trickle down into the C standard or C++ standard, and this helps everyone better take advantage of new hardware on a delay. So I think there's a lot to be said for the highest velocity things are de facto standards, things that are just adopted or get the attention of the public or the communities, and
Or more importantly, just get the job done.
Yeah, and some lowering in diversity of solution helps with making things portable, but then there's disadvantages of that too. In some ways, things would be really nice if LVM was our only compiler, but there's a lot of bad things that would happen if that were the case too.
Okay, thank you. One last question for Kristi before we stop here. Do you feel now more scared or more excited about, where we are going?
I'm pretty pessimistic with a hint of optimism. I say the optimism comes in when I know that we have, some really good tools. Umpire, one of them, to try to handle some of this, the architectures that we're faced with. But I think we will adapt. We're being thrown all of these crazy hardware, but I think the community at large will adapt. In time. Or we'll figure out, okay, that was a bad idea. Let's kick that out of there and go down this other route. But yeah, there's definitely some pessimism in there for sure.
It's a shame. You should be able to say you're excited because the innovation and the capabilities that are available to us today are unfathomable.
Oh yeah,
10 years ago, and so it's really sad that you have to be pessimistic about the outcome because you think it's going to be hard to use.
Cautious optimism is another way to say it.
That's not what I heard.
And really, I think
give me the red thing.
It's job security for us as well, honestly, which maybe is another thing to be very optimistic about.
There's a world in which AI can also help us with this. So if we think of the methods we're running, a lot of them are described in simple academic papers. In the state we hold in our minds before we create these systems are nowhere near as complex as the code bases that emerge. And what's happening is there's a weaving together of many different aspects, the system topology, the numeric method, the heuristics to handle resource allocation. All of this stuff's combined, but there are also learnable functions that can help the tool set out there. And if you think of how simple the mental models we have are compared to the implementations, there's something that down the road AI might also be able to help us with.
Okay, I tried to end with a user perspective. That was not to be. Let's thank all our speakers. And